So all of you welcome. Now we look at the review of the efficiency in packing, and also we try to look at a different way to look at the way solids pack themselves. Now we have seen earlier that in a simple cube, effectively there is one particle in a unit cell and its efficiency is nearly 52%. Whereas in a body-centered cube, effectively there are two particles and its efficiency is 68%. Whereas in a face-centered cube, there are effectively four particles and it is having highest efficiency of 74%. And also sodium chloride is ionic solid, packs itself in FCC pattern. Each unit cell has 4 formula units with 6:6 coordination. It means every Na plus is surrounded by 6 Cl minus, every Cl minus is surrounded by 6 Na plus. Cesium chloride has body-centered cubic packing with 1 formula unit for unit cell. So we made a study of this. Now we quickly look at the other way to look at the crystal patterns. The solid spheres, if they arrange themselves in one line, it makes an edge. Now the second row you can place just below. In this way, if you arrange, this packing is supposed to be least efficient because in this packing, as you can see, each particle is in contact with 1, 2, 3, 4 particles. And now this is called square close packing and it has a lot of wastage of space. Therefore, if there is a lot of wastage of space like this, it is not efficient. So square close packing can never be seen in solids. In solids, whatever the packing we see is like this. Can you see in this gap the particles are sitting? Now here if you see, here every particle is in contact with 1, 2, 3, 4, 5, 6. Hence it is called hexagonal close packing in 2 dimensions. In 3 dimensions, when you arrange the particles in this hexagonal close packing, you will be arranging it with 2 patterns. One is called cubic close packing, the other one is called hexagonal close packing in 3 dimensions. The cubic close packing, you can see, this is first row of spheres. And now, below this, second row of spheres sit like this. So that this gap and this gap will coincide. Can you see that? And on this you place a third row like this. Therefore, I call it as A, B, C. Again below you can put another sphere. Again ABC starts. This is cubic close packing is called ABC, ABC, ABC. Whereas in hexagonal close packing, what I do is, these are the 3 spheres. On this I place another sphere. On this I place another row again. So I call it as AB, AB, AB close packing. So these are 2 patterns observed from a different standpoint in the arrangement of particles. Both cubic close packing and hexagonal close packing are 74% efficient. So this is a note on the way the packing happens. And also when the particles arrange themselves like this, and in this gap if a third next particle is sitting, the small gap is called a tetrahedral void. When one row of spheres arrange like this, over them the second row of spheres sitting like this. Now this is a bigger hole generated in the packing. This is called octahedral void. A tetrahedral void is surrounded by 4 particles. Octahedral void is surrounded by 6 particles. This is small in size. This is big in size. Whenever particles arrange themselves in the course of packing, in any arrangement, maybe it is cube, when the particles arrange themselves in this pattern in 3 dimensions, in the course, whatever the packing you look at, it may be face-centered cube or simple cube or anything. In the course of packing, some gaps are generated. If n particles are making a lattice, a 3-dimensional arrangement of particles is called lattice. If n particles make a lattice, there will be 2n tetrahedral voids. It is fixed. And there will be n octahedral voids. And in case of ionic solids, where m plus and x minus are making a lattice, usually bigger ions make lattice, and the smaller positive ions sit in voids. So if you know how many voids are occupied, if you know what ions are making a lattice, you can actually arrive at the formula of the solid material you are talking. For example, when A plus B minus are making a lattice, B minus actually makes lattice, and A plus is there in all tetrahedral voids. What is formula? What is formula? You can say if x particles of B are making a lattice, then the tetrahedral voids will be 2x. Then A will be 2x, B will be x. Formula is A to B. You can think of other variants therein. That's all in this session. Thank you very much.